Good afternoon, everyone. Today we are very happy to have Brian Swingle from Brandeis to tell us about his work on effective field theory of chaotic spectral correlations. So Brian, please take it away.
Great, thanks a lot. Nice to see you all again, and thanks for the invitation. And yeah, today I'm going to tell you about some work that I'm doing primarily with my student, Mike Weiner, which is really broadly, I would say, about trying to understand the statistical properties of energy eigenvalues in quantum chaotic systems, and how the famous claim being that those statistical properties are like those of a certain kind of random matrix. And so we'd like to understand that, to have some kind of effective theory that predicts that, and lets us also compute corrections to it due to the fact that the systems of interest are structured. They're not actually random matrices. They have locality or symmetry or various other kinds of interesting properties. So that's broadly what this talk is going to be about. And I'll essentially claim that we succeeded in doing so, and I'll explain that as I go. So let me first introduce you to the basic topic. So as far as I know, random matrix theory in physics goes back all the way to nuclear physics and to the work of Wigner, who basically observed that there are a lot of complex quantum systems in nature, and they often have, as far as we can tell, a relatively unstructured energy spectrum, especially if you look far away from the ground state. And so Wigner's idea was, well, if you have this sort of unstructured spectrum, there's no regularities in it, then maybe you can model that spectrum using the spectrum of a random Hermitian matrix. So just take your Hamiltonian, throw away all the details, replace it by a random matrix of an appropriate type, and maybe that gives you a good tractable model of the spectral properties. And then, of course, this was a very nice idea, and it's been enormously developed over the years. And I also want to highlight, I use this, I'll talk about random matrix theory a lot. What I really have in mind primarily is Gaussian random matrix ensembles, which I'll define more properly in a second. There's a very big world of random matrices, of course, but what comes up most often in these contexts are just Gaussian ensembles. Okay. And here is like one of the classic, from this review article, a classic demonstration of the applicability and usefulness of this idea. What's being shown here are level spacings between adjacent energy levels of different nuclei with the same spin and parity, so the same symmetry structure. And it's a histogram normalized by the average level spacing. And you can see the histogram follows pretty closely to this kind of this hill-like curve here, which is the prediction of a certain simple kind of random matrix, a so-called Gaussian orthogonal random matrix. And by contrast, this decreasing black line is the prediction of Poissonian statistics, which is very clearly not appropriate here. So although you have some detailed fixed nuclear dynamics, you can actually capture the histogram of splittings using this random matrix result. So that's the really exciting thing. And of course, the subject developed since that time. For example, it came to be associated with the idea of quantum chaos. People were looking at classically chaotic systems, they were quantizing them, and then asking, what are the quantum signatures of that classical chaos? And one of the signatures that was understood, or at least conjectured, is that the energy levels of the corresponding quantum Hamiltonian would again look random matrix-like. And again, emphasize here, the conjecture stated in this famous paper, the Bohigas-Johnny-Schmidt paper, is that certain kind of strongly chaotic classical system would have a corresponding quantum spectrum that looked like that of a certain kind of Gaussian random matrix. Okay. So that was really for mostly in the context of few body systems with good semi-classical limits, but it sort of grew from that and became really a direct definition, one way of directly defining quantum chaos, even without any kind of semi-classical limit, where you just say a Hamiltonian, my favorite Hamiltonian is quantum chaotic if the spectrum of the Hamiltonian has statistical properties similar to that of a random matrix. And so here's an example. This is one of my favorite Hamiltonians, the quantum spin chain. It's an Ising's chain with Ising couplings between nearest neighbors and X and Z fields. This Hamiltonian is generically non-integrable as far as we know for generic values of the fields. If you turn off the Z field, it's integrable by free fermions, but if you turn the Z field on, it's not. And here in this barcode, I'm plotting all the energy levels for an 8-spin system. And you can see, okay, there's a ground state down here at the bottom, which is sort of special, -15. And there's also top states that are special. But if you kind of look in the middle of the spectrum here, where the levels are very dense, they look kind of featureless and unstructured. You know, there are some bigger splits, some smaller splits. And it turns out that in a certain precise sense, the levels here look like those of a random matrix. Now, for technical convenience, we can define from this Hamiltonian ensemble by adding, say, a small amount of randomness to, say, the Z component of the field. And this just gives us an ensemble of Hamiltonians that we can do proper statistics with. And again, the idea is we would call this Hamiltonian quantum chaotic if the statistics of this ensemble, even for very small values of the statistical of this sort of randomness here, would look like that of a random matrix. And if you compute various measures for this Hamiltonian, it will work. Okay, so this is a classic, simple example of a many-body quantum chaotic system by this definition. Okay, so in this talk, our goal essentially is to understand under what conditions this sort of random matrix behavior that I've been talking about is realized. And what I'll tell you about is an effective theory that my student Mike and I developed in this paper, and then also some follow-up work that extends this formalism to cases of symmetry and other situations. And the basic observable of interest is something called the spectral form factor. It's defined as follows. You take the time evolution operator U for some time big T. Big T is always time, never temperature in this talk. You compute the trace of it, which just means that you sum over all the return amplitude. So you start in some initial state, you evolve, you ask what's the amplitude to return. That's the diagonal matrix element. And then you sum over all states, right? So it's just a state average return amplitude. Then you square it. That function by itself for any particular Hamiltonian is a very erratic function of time. But if you average over some ensemble, then it becomes a nice smooth function that we can try to predict with some effective theory. And as I'll explain in more detail in a second, the characteristic behavior that is viewed as being random matrix-like is an intermediate time regime where this form factor grows just linearly with time with a known coefficient. So again, the question is, under what conditions is this behavior realized? It is realized if you take this model, for example, and compute that quantity, you'll see this linear in T growth for some region of time. And so we want to understand what's the biggest set of situations where this behavior is realized, and then also how do we calculate deviations from it, from structure. Okay, you know, in terms of when is this behavior realized, it was understood a long time ago, back in the 80s even, that one thing you needed was some sort of notion of equilibrium. In this famous Altshuler-Shklovsky paper, they observed that a certain observable was random matrix-like once you had time for the system for charge to diffuse over the whole system, right? So once you sort of reach diffusive equilibrium, once you reach global thermal equilibrium, then you could have this random matrix-like behavior. And before that time, you got something different. This kind of onset of random matrix behavior has also been investigated more recently in the many-body context. I've put a bunch of references here. Some of them we'll see again later. And this has kind of gone hand in hand with a lot of analytic results in the many-body context, where various solvable models ranging from spin chains in this famous Bertini-Coase-Prozin paper to SYK and Slide-Schenker-Stanford to a variety of other models and effective theories, where you can analytically calculate for the form factor and see that you have random matrix behavior in the appropriate regime. Okay. But you know, these are very nice results, but they still leave open the question of, you know, is there an effective theory? And also, in many cases, how do I compute the corrections to the behavior, to the random matrix structure? And the answer that we'll propose in this talk is going to be based on another kind of effective theory, an effective theory of hydrodynamics, which I'll call fluctuating hydrodynamics, which has been developed in a series of very nice works over the last, 5 or 10 years. Okay. And we'll explain all this a little bit later on, but just to give you a kind of broad picture of the landscape of ideas. And so again, our goal now is to, building on these works and building on these intuitions, we want an effective theory that predicts the ramp, this linear in time growth of the form factor, and lets us calculate corrections to that behavior due to structure in the system, to locality, conservation laws, whatever. And so the plan for the talk will be broadly broken into 3 segments. 2 of them are kind of shorter, and then 1 longer, where I discuss our theory in detail. First, I'll talk about these observables, a little bit more detail with the form factor, and also the idea of random matrix ensembles. Then I'm going to move and give you kind of an example. So I'll talk about locality and how conservation laws and slow modes affect the spectrum, how it causes deviations from the pure random matrix result. And then I will present to you our effective theory, which is based on fluctuating hydrodynamics, and show how it can be modified to give you an effective theory of the form factor. And then I'll talk about a bunch of examples. I'll revisit this diffusion example, which we talked about in the locality section. I'll talk about Floquet models, and I'll talk about symmetry breaking. Okay. So that's the plan. And yeah, please ask questions at any point if you have them. I'm very happy to discuss in detail at any point. But so for now, let's go on to the background. And let's talk about first random matrix theory. Okay, so the simplest idea is you have a Hamiltonian or some kind of matrix. I'll think of it as a Hamiltonian, where every element of that matrix is a random variable. We're going to impose some basic constraints on it, like that it's Hermitian. Maybe it has some particular symmetry, like universal symmetry, for example. Maybe it's real, etc. But we have a bunch of random variables, all the matrix elements, and we have a potential V, which determines a probability distribution over matrices. That's dP, probability measure. This is called a single trace ensemble because the potential, the weight is just given by a single trace of some power of the matrix or some potential function. And this kind of ensemble is nice because from this trace form, you can go to the eigenbasis of each element of the ensemble, and it reduces to a probability distribution over the eigenvalues. That is, the basis changes the matter. And you just have a distribution that descends from this, which becomes a distribution over eigenvalues, EI, which has the following form written here. And there's 2 important terms. First of all, the potential here becomes very much like an external potential at unit temperature in some statistical problem. If I think of the eigenvalues as like positions of particles, these are just particles confined in some sort of single particle external potential. But because of the Jacobian, which changes the basis from all the matrix elements to just the diagonal, to just the eigenvalues, this Jacobian induces interactions amongst the different eigenvalues. And particularly, you can see the famous level repulsion here. When a pair of eigenvalues gets very close together, this factor goes to 0, and so the probability measure is suppressed there. But it's really more than that. It's not just this nearest neighbor repulsion. It's actually also that there's essentially like a long-range force between different eigenvalues. If you keep with a statistical analogy and think about exponentiating this term to view it as an interaction between eigenvalues, it's like a long-range logarithmic potential between eigenvalues, sometimes called a Coulomb gas. And so what you really have is like a problem of a liquid in some external potential composed of particles which have this kind of long-range logarithmic interaction. And such a liquid turns out to be very stiff. It's very incompressible. And that stiffness is really what's being seen here in this linear ramp. A little bit more precisely, if you look at the form factor again, which I defined as before as the sum evolution operator here. And now I'm introducing one extra thing. I'm introducing something called a filter function, which lets us just zero in on part of the spectrum. So if you go back to this picture, the filter function could just say, like, let's select out the center part of the spectrum or some particular energy density and look at that part. That's a convenient technical tool. So just think about this F as picking out part of the spectrum. Then this form factor here is just this sum over pairs of levels. And so essentially it's controlled by the correlation function, the 2-point function, the pair correlation function between energy eigenvalues. And so if you think of energy eigenvalues as like particles following our liquid analogy, then this is like the Fourier transform of the position correlation function. So it's like a structure factor of a liquid. Like if you're scattering neutrons into the liquid or some kind of particle, this is or scattering light, say, this is what you would see as the response to a given wave vector, where the time t is like the wave vector. So the rigidity of the incompressibility of the liquid is showing up as some particular feature in the spectral response, in the essentially compressibility of this system. Okay, and so, just to give you a formula, if you take this random matrix ensemble and you compute the form factor for some general time t and filter function f, what you find is an integral over all the energy values in the spectrum, the filter function squared, because there's two copies here, the time t, and some numerical constants related to this Dyson index, which just is related to the symmetry. So you get this very universal formula, and in particular, if the filter function is localized in some part of the spectrum, this gives you a totally universal answer for the form factor. It doesn't depend on any details of the system except the symmetry. Okay.
Brian, can I ask a question?
Please.
About this Dyson index. If I see, because the on the bottom line, the formula is general, right? And then here.
Yeah, this is just the definition again.
Right. And in the ready the box, you had another expression probably that's for some specific model.
No, well, so this is for basically any model of this type here. Mm-hmm. Let's say for Gaussian models, you can do the calculation easily, but even for non-Gaussian potentials, it turns out this is still correct. The density of states is different, but this ramp part is the same. And so, yeah, this formula you can say derive relatively easily from a Gaussian random matrix, but it turns out to be very, very general. So like this formula would also be valid for that spin chain I wrote empirically if you do the numerics, say, of that system, right? So our goal is to sort of understand the origin of this formula or see how to get this formula from some very general point of view.
I see. But for example, for if we consider if we compare these two systems, like the spin chain and the Gaussian model, the difference is in the density function and well, okay, my question is that will the Dyson index be different for those two systems?
Well, the Dyson index just depends on the symmetry. So you would just need to choose the right kind of random matrix, like orthogonal, unitary, symplectic, etc., to match the symmetry. For that model over there, I guess is probably orthogonal. Well, yeah, we can. Yeah. Anyway, so you would choose this. You would choose the random matrix based on the symmetry, but apart from that, it wouldn't matter.
Okay. So I got the idea. This Dyson index depends on the model you're looking at.
It depends on the class of models, I would say, but it doesn't depend on the details. It just depends on whether it's controversial invariant or not, something like that.
I see. Thanks.
Yep. Okay. So just let me just make a definition here, just to flash something quickly. So there's an important idea of a Thales time, which is essentially the time for the random matrix behavior you saw in the previous slide to become valid. So at very short times, say in this region here called the slope, all the details of the system matter. It's not universal. This form factor just has some system-dependent answer. And so we need to wait some time for those system-dependent details to wash away, and that time is the Thales time. And for a variety of reasons, it's nice to focus on what we call the connected form factor, which basically just subtracts off, if the form factor is like the average of the square, this is the square of the average. So we're subtracting that off, and it's just like looking at a variance, basically, of some random variable. Okay. So what I plotted in orange here is the connected part, and you see it just grows linearly in time for a very long time, and then has a dimensional saturation set by the total size of the Hilbert space. And so we kind of remove this slope part, which is related to the density of states, and just get this very pure linear growth. And then in a actual system, what you'll see is at an early time, there's deviation from this linear growth, but then eventually it approaches it at late time. And the time scale for that approach to happen is the Thales time. So let me just flash again the goals. There is essentially 4 regimes of time we can identify. There's very early times where things are very non-universal, and that can be interesting depending on what your interest is, but we can't hope to have a very universal effective theory there because it depends on all the details. Then at very late time, there's also this plateau region and the ramp region, which are just determined by very simple properties like the symmetries and nothing else. And then the novel feature that you find in many body systems, say, with structure, is that there's also what I'll call hydrodynamic regime, where the universal slow modes of the system are giving you some essentially or relatively universal corrections to the random matrix behavior, which we can actually calculate, and which don't depend on the details too much, except insofar as like, what are the number of modes, what are their dynamics like, etc. So think here, diffusion, sound, Goldstone modes, that sort of thing, which are slowly evolving modes and can control the crossover to the ultimate fully equilibrated random matrix-like behavior. So our goal is basically to understand these two red regions. And more generally, you might want to understand these things and also relate them to other ideas of quantum chaos. For example, out-of-time order correlators or eigenstate thermalization. There's all kinds of other things people associate with quantum chaos. I won't talk about that here, but that's something you might want to do. And then, one of the things that this theory should do for us is compute the Thales time and also compute the putative universal behavior in this hydrodynamic regime. And the basic picture you should have in your mind is of these 2 rings, which are like the 2 copies of time evolution. Imagine at each moment in time, you have some kind of fixed evolution, and the evolution is repeated over and over and over again. That's why there's the same elements repeated. And these black lines represent averages or sort of correlations between forward and backward evolutions. And the idea is you can kind of correlate them in this way or in any shifted way. And so this space of shifts is essentially what gives rise to the linear in time growth of the form factor. But at earlier times, this is not like a rigid identification. There's actually kind of fluctuations and flexibility in its identification. And that enhanced flexibility gives an enhancement to the form factor, which we'll be able to calculate in terms of hydrodynamic degrees of freedom. Okay. So let me now go, if there's no questions, to give you a first example of what's going on, just to try to get our feet wet. I'm just going to talk about the impact of locality. So imagine you have that spin train I showed you, or whatever your favorite quantum system is, extended quantum system. And imagine you break all the other symmetries explicitly. You add disorder, you add a random potential, you break all the other symmetries, such that all that you have is energy conservation at the end of the day. In such a system, sort of the minimal slow dynamics would be diffusion of energy. So everything else is going to relax quickly to its equilibrium configuration, all other observables. But energy density, because of locality, because of energy conservation, has to evolve slowly. And the simplest kind of evolution that you can have is energy diffusion. Here's I'm showing you the diffusion equation for some energy density epsilon. And what this equation predicts is that if you look at very long wavelength fluctuations of energy, they decay to equilibrium, that is to 0 amplitude, very slowly at a rate proportional to the wave vector squared, or 1 over the wavelength squared. So in particular, for fluctuations that are of size the total system, it takes a system size dependent amount of time for them to decay to their equilibrium value. And I claim what this means is that at some given time t, in the limit of a large system, there is an extensive number of almost conserved quantities, right? You fix a wave vector, case of t, which is set by the diffusion constant d and the time t. And if you go back to your diffusion equation here, what this will tell you is that all the modes, all the energy fluctuation amplitude modes with wave vector less than kt have barely decayed. They've decayed by like less than 1 e-fold. Okay. So all those modes have barely changed from their initial value, and that means they're nearly conserved, right? And we can count them, just count the number of modes, and we'll see that it's extensive, proportional to the volume, and some factor of this characteristic wave vector to the dimension of space. Okay. Now, if you think about the Hamiltonian, if you have a bunch of modes or a bunch of sectors that are all conserved, that means there should be no matrix elements between these different sectors. And so it can't possibly be that the Hamiltonian is just one big random matrix. At best, it could be a sort of block sum of lots of small random matrices, right? But then you can go back to your form factor calculation and say, well, what if I didn't have one big random matrix but a sum of two small ones, a block diagonal sum? Well, then the form factor would just be enhanced because it's like a variance, and variances add over independent random variables. Right? So basically, you should get a ramp, so to speak, for every conserved sector, not mode, but sector. So sector is labeled by the amplitudes of all the modes. And you would just get some big enhancement to the ramp coming from this large but time-dependent number of almost conserved modes. Okay, so what you would expect is a ramp, but roughly speaking, enhanced by a factor of a number of sectors, which is roughly like e to the number of modes. Because for every mode, I can choose the amplitude. And so you're like specifying a mini body state by giving the amplitudes of all the single particle excitations. Now here's a more precise model, which we cooked up to describe this. Imagine you have a situation where you have a bunch of sectors that are decoupled to first approximation, labeled by alpha. And what this decoupling means is the Hamiltonian is a sum of a block diagonal thing. So these gray blocks are the sectors here. They can have states within them, but they're decoupled from each other. And then some perturbation V, which connects the sectors, but which is weak in some sense. And if you ignore the V, what you would expect, what I just said, is that the form factor would be the random matrix result, essentially times the number of sectors at a given energy, integrated overall energy. In other words, you're just counting up the number of these blocks, and each block gives you an independent ramp. But what Mike and I showed is that you can include the effect of V in perturbation theory. If you say assume these gray sectors are random matrix-like, and you do a straightforward calculation, essentially boils down to Fermi's golden rule, what you can show is that including these transitions from the perturbation gives a generalization of this formula, which takes into account the dynamics, which says that the form factor is a sum over sectors, the filter function that's always there, the form factor within each sector, which if the sectors are random matrix-like, is just this universal T over 2 pi, say. Here I've chosen unitary ensembles, so the Dyson index is 2, but you could carry that around with you. And then there's one extra factor here, which is the return probability. So the probability to start in a sector and after a time t to return back to that sector, right? So in other words, it's the probability to start with some particular pattern of long wavelength energy fluctuations and to, after some time t, to come back to that same pattern at the end of the day. So we derived this formula. And we can use it now for this diffusion case to calculate. So if you can easily, from the basic equation here, figure out what the probability of an amplitude EK final energy fluctuation of wave vector K at time t is. You can see if you start with amplitude EK, it decays by some amount, right? And so it's a Gaussian centered on that value. And there's a width, sigma square, which comes from this noise term, right? If that noise weren't there, you would never be able to come back to yourself, right? Because you just decay, and then you would definitely not have returned to the initial state. So the noise is actually important. The fluctuations are important to make this work right. But anyways, you get this nice Gaussian answer here. And now if you set the final energy amplitude equal to the initial one, that's the return probability, right? And integrate over initial conditions, remarkably, the variance cancels out. And you get this very simple formula, which depends only on the decay rate. And now if you want to sum over all sectors, just like if you were to sum over all many particle states of like a bosonic field, you would sum over all the single particle levels of each mode and then product over all the modes. We're doing the same thing here. We're now multiplying over all modes of this decay factor for each mode. And then you put it everything together, you do the calculation, assuming K is continuous, and you get this nice formula here. which if you compare to what we had on the previous slide is almost the same up to an overall numerical factor. So on the previous slide, the number of modes was given by this, where KT is, again, this 1/squared of dt. And now basically just the d is replaced by a zeta function here. So up to some numerical factor is exactly what we expected to get, but now it's a fully correct calculation, at least within this weak transition model. And you can go say and ask, okay, if I want to be close to the random matrix result, which means I want this exponential here to be close to 1, or I want the argument of the exponential to be close to 0, then it just means I need this factor here to overwhelm the volume factor, right? Which intuitively just means I need to make sure that even the slowest mode, whose wave vector is set by the system size itself, even that mode has decayed significantly, right? Because if that mode's decayed a lot, all the other modes will have decayed as well. The wavelength of that slowest mode is just the system size. And so its decay rate is system size, let's say its lifetime is system size squared over the diffusion constant. So this is like the lifetime of the slowest mode. And there's an extra little log factor which says that we want this sum over sectors to be within epsilon of 1. Okay. So if we want to be epsilon close to the random matrix answer, we just need to wait a time, which is essentially set by the lifetime of the slowest decaying hydrodynamic mode, the slowest decaying diffusive mode. Okay. And moreover, you see that if I plot this function as a function of time divided by L squared, that I actually get a universal function independent of either time or length independently, but just a function of this one scaling variable. Okay, so that's a prediction of this formula. Now, some other people, not us, but another group, Friedman et al., actually did numerics for a spin chain. Not for energy diffusion, but for charge diffusion, but the arguments still work that I gave previously. And so what this plot is showing here, this is their data taken from this paper. It's the logarithm of the form factor divided by time. So they're taking out the overall ramp. They're taking the ratio of the form factor divided by t. So they're taking out this factor of time here, and they're just going to get essentially the return probability, which is this formula, and they're taking a log of that. So essentially they should be plotting what's inside the brackets here. And they're plotting that as a function of time over L squared, right? Which is sort of the scaling variable I was discussing before. And they look at a bunch of different system sizes from 12 to 18. And what they observe is that if you plot this observable versus the scaling variable, you more or less have scaling collapse, especially at the larger sizes. So red, green, and dark blue are kind of all pretty close to each other, which indicates that you've identified approximately the right scaling variable, and all these different system sizes collapse onto one universal curve, which is what the previous formula predicted. And then the black line here is actually the fit of this data, of their data, this is their fit, to this formula here. So they fit the diffusion constant to match this data, and they see that the fit works reasonably well, right? There's a little bit of deviation here, relatively early time, but especially at late time, it looks pretty good. And these authors also derived that formula that I wrote in the previous slide in 1D from using a different technical tool, something called large on-site dimension. And what we're showing here is that this formula arises very generally just from the assumption of diffusion. Okay. So this data is not for large dimension, it's for like a qubit model. And so from that point of view, you could say, well, why does this large dimension result apply to the qubit model? And what we're saying is, well, you don't need any large dimension assumption. All you need is diffusion. And diffusion alone immediately predicts this behavior. And as I'll show you in a second, we can actually even compute corrections to it to understand maybe why it works so well in this case, or help us understand that.
Brian, hey, I have a question. Maybe I missed it. So what was the physical underpinning of the diffusion equation? Was it a postulate, or like were you able to derive it from?
Yeah, I'm just assuming it's the case here. I'm just assuming it.
Okay.
Of course, I would say what you're touching on is a very important question, which is how do you actually get diffusion out, or how can you predict diffusion itself, or how can you compute the diffusion constant? And that's of course a very important question. And so the way I like to think about it is something like this. For our purposes here, you could imagine the following. Suppose I assumed that my system had some kind of random matrix-like structure. Suppose I assumed it could be built out of clusters, each of which is like a random matrix. You know, then presumably it would be possible to derive the diffusion equation from such a very strong assumption, or whatever the appropriate transport physics was. And what I'm kind of showing here is that you can go the other way. If you have the diffusion equation, that implies that, or that will imply, according to our effective theory, that the system can be thought of as these chunks of random matrices that congeal together to one big random matrix at long time. So it kind of goes both ways. But here, for this argument, I'm assuming this equation, and I'm assuming that the form factor within each block, each sector, is random matrix-like. And that'll be the gist. Basically, we take the hydrodynamic effective theory and we use it to calculate spectral properties.
Thanks.
Okay, so without further ado, let me describe the actual theory and then give some examples. Let me start with some intuition. So on the lower picture here is what we want to calculate. That's the form factor. It has, again, this sort of forward evolution in red and backward evolution in blue, where the tail meets the head, right? You come back to yourself. So this is the return amplitude on the forward contour, return amplitude on the backward contour. And the idea is that this set of time evolution contours looks an awful lot like the Schwinger-Keldysh contour, or the NN contour, or the closed time path contour, where I have some initial state in purple. I evolve it forward in time, take a trace, I connect the forward and backward, and then I evolve it backward again. And what that calculates for you is this quantity, just the trace of the time evolution of some state rho, which is the purple thing, where I allow the forward and backward evolutions to be different. Right? And you can think of this as like this is sort of like a mathematical tool. It's a generating function, which you can use to calculate real-time response functions in your system, right? And this is a standard tool now in the effective theory of hydrodynamics, in which you can formulate that effective theory. And our idea is that whatever the effective theory is here for the Schwinger-Keldysh contour should also be related to the effective theory, whatever it will be for this form factor contour. In other words, it makes sense that hydro is going to play a role, because hydro is what controls the long wavelengths, long time physics on the Schwinger-Keldysh contour, and so it should also control the physics suitably modified on this form factor contour. Now, let me very quickly review this closed time path formalism, just to be super fast. So just to give you a flavor, you won't be able to digest this, I would say, but just to give you a flavor. The idea is basically you want to calculate this generating function from which you can, suppose you say couple on the forward and backward contours your conserved density to some background field. And if you calculate this generating function as a function of that background field, you can use it to calculate any time-ordered correlation function you want. You can also calculate response functions, etc. So you can get all the physics out, and particularly you can get the physics of hydrodynamics out if your system has it. And it's convenient to take these two copies of the fields, the forward fields and the backwards fields, and turn them into a different basis, the symmetric and antisymmetric basis, which are called classical or R-type and quantum or A-type, depending on your community. And the idea is that from the structure of this contour, there's a very powerful set of rules that govern the allowed effective actions you can formulate in terms of these R and A-type variables. So just to use this energy diffusion example again, the R-type variable is ultimately going to be essentially the energy density. And the A-type variable, which I've called phi A here, is, if you ignore the quadratic and phi A squared piece in this action, is roughly like a Lagrange multiplier that enforces the equation of motion, which is the diffusion equation, right? So if you ignore the quadratic and phi A squared piece, this action just says phi A is a Lagrange multiplier, and its equation of motion is the diffusion equation for energy density, right? And then what does this phi a squared term do? Well, if you imagine, for example, uncompleting the square in the usual way, doing your path integral trickery, then phi a will again appear linearly, but now that'll be essentially a random source for the diffusion equation. And so phi a is still a logarithmic multiplier, but now it's essentially encoding the not the deterministic diffusion equation, but the stochastic diffusion equation, the diffusion equation plus noise. And again, you know, the point of this is there's all kinds of rules here, so that if you're making a derivative expansion in gradients, in time derivatives and space derivatives, that's what this triangle is the spatial Laplacian. That there are lots of powerful rules, like every term in the action has to come with an A-type variable. The terms in the action with an even number of A-type variables need to be imaginary with a certain sign, et cetera, et cetera, et cetera. Okay, so if you just write down an effective theory according to these rules, this would be the simplest action you could write. And so diffusion would naturally come out of that. Right? Of course, there can always be other terms, or this term could vanish for some reason, but the idea is that this is a set of rules for which you can do effective field theory, and for which standard hydrodynamics is the leading prediction. So our proposal is the following. Imagine you have some hydrodynamic effective action for the Schwinger-Keldysh contour at some scale where you've integrated out the fast fields and kept the slow fields. So there's some energy scale or some time scale. You've integrated out all the things that decay faster than that. You've kept the slow modes. That scale, that fast scale, is short compared to the overall length of this interval, but it's fast compared to the lifetimes of all the slow modes. And our idea is the following. At that cutoff fast scale, the effective action in the bulk of these contours here will be identical between the Schwinger-Keldysh case and the form factor case. So the effective action in the bulk will be the same in the two cases, with two modifications. First of all, the boundary conditions are different in the past and the future. So there's no state here, and we're not gluing together the future and the past. We're gluing the forward and backward. We're gluing the forward to itself and the backward to itself. So the boundary conditions on my fields will be a little bit different. And I don't have this initial state. So what I have to do is I modify the boundary conditions and I sum over different states. So in other words, different values of the energy, overall energy density here. The initial state essentially sets the energy density, the other values of conserved charges. What I should do in this form factor case is integrate or sum over those different possible values. And then I also need a technical assumption that there's some averaging like disorder that connects these contours, because otherwise, as I said, there's some erratic function of time, and you wouldn't be able to predict that with this simple theory. So in this case, the initial state does that for you, but here some disorder averaging will correlate, if you like, the fluctuations or the instances on both sides and give you this nice solution. So here's just one more kind of summary picture of what it looks like. In the top left, we have the Schwinger-Keldysh case. So this is the microscopic situation where you have the thermal contours for Perry's initial state, the forward contour and the backward contour. And in the bottom, I'm showing you kind of the effective action point of view, where you have a forward contour and a backward contour that seem coupled. And you have some kind of hydroeffective action, which depends on the energy. The background energy density is set by this thermal state. And now on the right, on the top, we have the microscopic form factor contour with the forward and the backward. And the bottom right is our proposal for the effective theory, which is you take the same effective action over here, you modify the boundary conditions, and you sum over energy, right? Because you don't have this initial state, the thermal state anymore. You're just summing over all possible states. So you have to sum over all possible energies, background values of the energy for this theory. Okay. So let me show you that it works. The proof is in the pudding. Yeah.
Just to make sure I understand it, your last patch.
Yes.
The right bottom one. So this case, when you sum over all the energies, you mean TO, the cutoff momentum, or it's really all the energies?
I would say just think about summing over all possible energy densities in your theory. So like it's like the background value of the energy, or summing over temperatures, if you like, of this thermal contour. Because remember, the form factor had this sum over all states in it. We can use a filter function to zero in on some spectrum, some part of the spectrum, but in principle, we just sum over all states, right? So that's what we're doing here. We're summing over all states, and a given state has some background value of total energy, which sets the effective temperature of that state, and I'm summing over those things. And then for each like background energy, I have this hydrodynamic theory. The diffusion constant, for example, can depend on the background energy density, etc.
Okay, that's good. But is there any relation of this sum with the previous sum that you showed? We have to sum over different sectors. Are these two things related, or
yeah, in some sense, like this is part of the sum over sectors, in the sense that different energy windows are different, like different sectors, basically.
Okay.
But it's I would say it's mostly, you should mostly think of it as a different thing.
Mm-hmm. I see. Thanks.
So let me show you how it works. So suppose we focus just, yeah.
So Brian, one more question. So the fact that as you said, in the case of the regular emergence of hydro from the Swingle contour, right? You had the thermal state that correlates the two contours, and like they're connected via the fact that you start with a thermal state.
Yes.
And in the spectral form factor case, it's the random matrix character that correlates them, and that you get this hydroeffective action sort of in between them.
Yeah, I would say it this way, like the role of the thermal state is to set the values of conserved charges, and to ensure that although on the forward and backward contours you have some detailed microscopic state, it's the same state on the two cases. Like that's the kind of microscopic correlation that this thermal contour does for you, or any initial state, basically. Like it's like, think of it as a thermal field double.
Yeah, sure.
Correlating two sides. So here, the sum of our energy takes into account the fact that we don't have a fixed background value of conserved charges, and the averaging is what forces us to focus on the like diagonal or equal fluctuations on the two sides. So that's how we need that averaging in that case.
I see. And one more question about it. So if you think about say holography, you can think about hydro modes emerging as Goldstone bosons, coming from the connectivity of the bulk between the two boundaries that without thermal state would not talk to each other. Is there a similar picture that you can develop, like in the case of the spectral form factor, or like that's like the sort of the nature, understanding the physical nature of the Goldstone bosons?
Yeah, I think probably so, but I have not thought too much about it. But yeah, I think it, yeah, I think so.
Yeah,
and in particular, I'll make one other comment, which is that this also kind of connects to this factorization puzzle story, because this hydro action kind of has a factorization puzzle for it. Like, I don't need to say anything explicit about averaging to just do the calculation I'm going to do in the next slides. Now, you definitely need to do it. It doesn't really make sense otherwise, but the sort of hydro theory, it wants to be an average theory, and you need to like, tell it that, or somehow, yeah, anyways, there's a bit of a puzzle there. I mean, not really a puzzle, but like maybe a place for further elaboration of the role of disorder.
Yeah, thanks.
Okay, so yeah, so let me just convince you that it works, and then I'll do a few more examples very quickly. So suppose we go to very long time, everything's diffused away, and we have just global thermal equilibrium. Then I go to my effective action, I drop all of the spatial gradients. Everything is now uniform in space, and I get this simple action, which just has the electron multiplier field, phi A, the A-type field times the 100 of energy. And what this action tells me is that energy is conserved. Okay, right? That's the equation of motion, is that energy does not change in time. Perfect. And all of the finite frequency modes of this thing just enforce energy conservation. However, the zero modes are special, the zero frequency modes. In the case of the Schwinger-Keldysh contour, the zero frequency mode of phi A must be 0, right? Because you can think of phi A as like the relative time between the two contours, and because the contours have to meet in the future and agree, the relative time shift there has to vanish. And since that received a contribution from the zero frequency mode of the relative time shift, that zero frequency mode has to vanish as well. But in the form factor case, it's not true anymore. There's no constraint that the time shift between the two contours must vanish in the future. So this zero mode now becomes a free variable that we integrate over. And its domain of integration is, since these are circles, it's itself a circle of size the time, right? So the integral over the zero mode here is just the time, and the integral over the zero frequency mode of the energy is just total energy. And so we actually exactly get this time times integral over energy factor that we had in the random matrix case. And if you go through and regulate your path integral carefully with all the 2 pi's and do it in a sensible way, you will actually get exactly the, say, 2 pi that you would have for a random matrix in the unitary the unitary ensemble. Okay. And moreover, you can actually even use this to compute higher moments by sort of making pairs of these hydro contours, so to speak. And that gives a certain prediction, which is a Gaussian prediction. And that's also what you would expect from a Gaussian random ensemble. And it's also what you would see if you look, say, at that spin chain that I showed you many slides ago. So we were sort of surprised by this at first, but in retrospect, I guess it had to be this way. But actually the theory predicts random matrix behavior at late time already. But by including all of the finite wave vector modes, we can also compute all the corrections. So I take that effective theory that I wrote a couple of slides ago, this one here. It's a Gaussian theory, so I can do the path integral exactly. I do my regulation, here's my action, I do all the calculation, and what you find is that the form factor, or at least the enhancement part of it, is some product over modes. And I exactly recover the formula I argued for you based on sort of Fermi's golden rule in our simple toy model of blocks. I get exactly that formula back from this, this hydro calculation. So it knows about all that physics. So the takeaway here is that it predicts the late time ramp and actually calculates corrections to it. So it's doing exactly what we wanted our effective theory to do. Now, what's also nice about this theory is that we can include interactions. And relative to the usual Schwinger-Keldysh story, there's new complications because you have time periodicity. So any fast mode, any mode that decays more rapidly than the length of the circle, is going to be more or less as it was in the Schwinger-Keldysh case. But slow modes, modes that can wrap the circle, are strongly modified. So you get all kinds of modified correlation functions at quadratic order from wrapping of your slow modes. These can give many effects, including enhanced infrared effects. But at the end of the day, you can, formulate this theory and compute imperturbation theory. And as I'll show you in a couple of slides, you can just compute, say, the leading order correction to that diffusive quadratic theory, and you can see that it's small at late time. So we can compute corrections and we see that they're small. Now let me just flash a couple of other things. One thing we can do is consider Floquet models. So these are models where you have a time-dependent Hamiltonian which repeats every period. Here, capital omega is the frequency of that repetition. And actually, the data I showed you before from Friedman et al. Was data for a Floquet model. And one thing about such models is that they're described not by random Hermitian matrix ensembles, but by random unitary ensembles. In this case, in this paper, it would be a circular unitary ensemble. And that also has a ramp with a different coefficient. In fact, just a coefficient of 1 times the number of periods. And that we can also derive from our theory. We take the same hydrodynamic action, but now take into account the periodicity of the Floquet energy. And that predicts that the form factor in this case will now be just the number of periods that you have. And that's exactly what they see here. But more than that, we can say, in this context, calculate one loop effects. That's what I was alluding to before. The data that I showed you here is for a model at half filling, where there's an equal number of, or the charge density is in the middle of its allowed range. This simplifies some of the interactions a little bit, and you get this set of leading order non-Gaussian entities in the effective action. And we can just do a one loop calculation using those Green's functions I wrote before, and you get some answer. Okay, so the one loop correction to the form factor is given by this expression. I don't want you to really to digest this or worry too much about the details, but we can just calculate, you get some answer. The important thing is I can think of the form factor as changing by a factor of e to the I times this average. And that has the form of some constant over the scaling variable. Here u is t over L squared, so that's the scaling variable we saw before. This is the same scaling as the quadratic answer, so that you can think of it just some kind of shift or correction to the diffusion constant. But there is a correction that violates the scaling. That's the C3 term. And but when you phrase it in terms of this dimensionless variable, you can see that system size suppressed. So at large size or at long times and fixed sizes, this term is going to be unimportant relative to this one. And so the one loop correction is present, and you do actually weakly violate the diffusive scaling, but the theory predicts it's a small effect. Okay. So we can actually go and calculate now, what would be the first correction to that diffusive theory. And we see that it's small, let's say in this regime out here. And so maybe that helps us rationalize why the diffusive description will work so well in this region. Now, the final thing I want to mention very briefly is additional symmetry. So if a Hamiltonian has some other symmetry, like some unitary symmetry, then the typical thing that happens is Hamiltonian decomposes into blocks, diagonal blocks, or sorry, it's a block diagonal decomposition labeled by the irreducible representations of the symmetry, right, the irreps. And if you just take your random matrix theory and add the symmetry to it and assume all the irreps are uncorrelated, which is the generic case, then the prediction of the form factor is just you sum over the irreps, the dimension of the irrep squared times this same ramp. And the physics of this is just that each irrep is different, but within a given irrep, you have a number of copies of the same random matrix, the dimension of the irrep number of copies. They're all perfectly correlated, and so this is a variance, and you get the number of copies squared. And in one of our follow papers, we said, well, what happens if you have symmetry breaking? And physically, what this means is, again, you have some slow dynamics, like an order parameter dynamics, which is frozen or very slow. That means there's matrix elements that are suppressed. And so what happens in terms of these irreps is that different irreps become correlated due to the suppressed matrix elements. So here's a simple example with Z2 symmetry. Imagine some kind of double well. Then within each well, you have some sort of random matrix structure. But the Z2 symmetry of the double well implies that whatever the random matrix is here, it's also the same as the random matrix there. And if you have strong tunneling between the two, then those two things will split. You'll have the even and odd parity sectors, those are the irreps, and they'll be independent. But if the tunneling is suppressed, then these two sectors are just the same. They can't split. And so you're going to have an enhancement of the form factor. In this case, the unbroken case would correspond to a factor of 2, because the dimension of each irrep is 1. And there's 2 irreps. And the broken case would correspond to a factor of 4. And using all the same ideas that we discussed before, we can compute essentially how you would cross over from the broken case to the unbroken case at very long time. Sort of if the system ultimately at long times restores a symmetry in a finite size system, we can calculate that crossover. You have the same kind of similar sort of story. One interesting feature is that the return probability formula is more complicated now because you have correlations between the different blocks. But anyways, we can derive some formula with various kinds of dynamics. And here in this plot is just showing you the comparison between our derived formula, which is the orange, and some numerical data for a system with Z20 symmetry. That's the blue, and they just agree perfectly. This gray line is 20. which is the late time value. That's the sum over these representations. The dimension of each irrep is 1. So you just get a sum over irreps. There's 20 of them, and you get a factor of 20. Okay, so that's this late time 20. Up here, 400 would be 20 squared. That's the totally broken case, and you're seeing a drop from the broken case to the unbroken case. And our theory can correctly calculate this drop. You can, of course, also do continuous symmetries, non-abelian symmetries. We actually discussed all those cases in our paper, and we can get agreement with numerics in essentially all those cases. So with that, I want to wrap up. What did I tell you about today? Basically, I said that there's sort of a growing set of connections between different manifestations or features of quantum chaos. Quantum chaos itself is an interesting subject, and we don't all agree on what exactly it should be defined as. But there's all kinds of connections between different possible definitions, and maybe there is just one overall framework. That's what I think anyways. And today I showed you essentially how thermalization and hydrodynamics relates to or lets you calculate spectral properties. So it sort of implies random matrix-like structure. And in concrete terms, I gave you tools. I've explained to you tools you can use to calculate form factors in systems with slow modes. And I gave you some applications to a Floquet model for which there's numerical data, and I also discussed symmetry breaking a little bit at the very end. Right? And I just want to emphasize again, this effective theory is very nice in that it computes the corrections, but it also predicts the random matrix behavior at long times. And it really is a proper effective theory in the sense that we formulate this well-defined effective theory on the Schwinger-Keldysh contour, which is, by now known to be a totally sensible effective theory. We then make these modifications to go to the form factor contour, which are all well justified, I would say. And then that modified effective theory computes for us spectral properties. So I claim for the first time that we really have a proper effective theory that predicts very generally random matrix behavior just from the assumption of fluctuating hydrodynamics. Okay, so of course you still need to derive that if you want from some other thing. But if you grant me that, then I think random matrix behavior and the corrections to it follow. And although we might want to derive the details of that theory from microscopics, at least the form of the theory is a proper effective theory. That's the sort of leading order thing you would write down for some system given a set of symmetries. Okay. And there's a lot of directions for future work, including higher cumulants. I showed you the moments, but you can look at cumulants to see deviations from Gaussianity. That's interesting to think about. And there's, I think, more to understand about the role of interactions in these theories. For example, in our paper, we showed that if you sum a certain set of diagrams, you can strongly violate that diffusive scaling. That's probably something you can only observe at very large size and some kind of intermediate window of time. But it would be good to understand better if that's all that can happen or there's more surprises out there. Okay. But let me just say thank you. Happy to take additional questions.
Thanks for the wonderful talk, Brian. There are many ingredients, so I think there should be a lot of questions that will pump out. Maybe I can start with my question. So somehow I got lost maybe at some point that we talk about hydrodynamics, but this hydrodynamics will describe the whole like ramp plateau or just certain region of or before the ramp.
Yeah, that's a good question. So it would describe, where's a good picture? Yeah. So like it would describe the ramp, and it would describe corrections to the ramp at sort of intermediate time from slow modes. It would not describe very early time things, and it would not describe the plateau, which is some like ultra long time, sort of e to the system size kind of time scale. So it's really like this ramp regime and the hydro regime that it's capturing, and not the very early time and the very late time regimes.
Okay. So this hydro regime is really some regime interpolating the plateau, but somehow when people talk about chaos, they really mean that there is a ramp and plateau, right?
Yeah, that's right. So, I mean, the plateau, I mean, the ramp we get, of course, that's what I argued for you.
Yeah.
The plateau is not, directly visible from this calculation. From a certain point of view, the plateau is kind of boring. I mean, microscopically, it's very simple to see how it comes about. But from the point of view, this kind of semi-classical or path integral sort of approach, it's actually not easy to see it. So I would say from this point of view, it's, you can see that things are going to break down at that time scale, but to like really properly compute the answer is not something that we've done yet with this approach. So that's an open question, I would say.
I see.
If you just say, okay, it looks like a Gaussian random matrix, you can compute all the moments and they look like those of a random matrix, then it has a plateau. But there's no direct calculation in this language.
I see. That's interesting. Can I ask one more question?
Please.
Yeah, about this one loop correction that you have. So
Yeah.
if that correction is really correcting like this fluctuating part before the around the beginning of the plateau, or like that correction will correct which quantity?
Yeah, it's like a correction to this. Like, so here I'm plotting the log of the form factor divided by time.
Mm-hmm.
So at a long time, this goes to 0, which corresponds to a form factor just being perfectly linear in time. So it's just representing some enhancement of the form factor that's decaying, right? And without that correction I computed would be valid in this region, right? So if you look at it, at very long time, it goes to 0. So just imagine this thing in brackets here as correcting this curve. That's what it literally does. So it would change a little bit the value, like just the overall size of the black line, and also add a different time dependence in there coming from this.
Okay.
Right?
Okay.
But you can see that at long time it vanishes. Both of these things vanish at long time.
I see.
So it still decays back to the fully thermalized state, so to speak. But it would change how you approach that state.
I see. Presumably these C2 and C3 are like a small parameter related to some coupling or
yeah, I mean, they enter in this effective action. Mm-hmm. So like, C2 is related to G, which is one of the couplings here, and the cutoff, lambda sub K, and some factors of diffusion constant in time and so forth, right? So C2 is basically proportional. I mean, they're both proportional to G. I think the G prime term vanishes in this case for this particular calculation. So it just goes to this G term. And the meaning of these terms, they have different kinds of meanings, but like these terms can arise, for example, from the fact that the diffusion constant depends on the charge density. So if you imagine a fluctuation in charge density, that actually in principle changes the diffusion constant locally, right? And that represents a nonlinearity, basically where higher moments of the higher powers of the charge density are coupling. If you look back at this effective theory here, if you imagine this D were itself epsilon dependent, mm-hmm. then you'd have nonlinearities, right? You'd have right. Cubic or higher nonlinearities, right?
Right.
And that's what. So that's an example of the effects that these kind of terms here are incorporating.
Okay.
This effect here, for example, the G effect is coming from the fact that the diffusion constant is maximal, or let's see, minimum. Well, anyways, it has a local extremum at half filling, and then as you go away from that, it evolves quadratically. So that's why there's no rho squared term, only a rho cubed term. This is basically the diffusion equation where the diffusivity has been expanded as a constant plus a rho squared piece, and that's what this term is.
Okay, I got it. Okay, so this basically is a correction, as you said, to this diffusion constant.
Yeah, and this term is like a correction to the compressibility.
Okay, I see. So
all the fluctuations.
Okay, I see. Okay, that's interesting. I see. Thanks a lot.
Yep.
Brian, I have a question about so you have hydrodynamic regime that goes to the ramp and then it breaks down at very late times, and the spectral form factor saturates. But before the hydro regime, in systems like, say, holography, you have transient effects that actually you can put under control. I mean, like something that is evolving, you know, say exponentially decaying in time with some known frequencies, say quasi-normal modes of black holes. So do you have such effects here that you know that happen, you know, in the vicinity of the transition to the hydro regime?
Yeah, I mean, in principle, you could include such things.
I mean, that's where this is where the regime in other types of dynamics, which is no longer universal in the sense that it depends strongly on initial conditions. But then, like when you look into more detail, it's in some cases, at least, it turns out that there are simple regularities, right? Like maybe you need to add like 1, 2, 3, 4 corrections, and like that takes care of most of the non-universality.
Yeah. So yeah, I think that's a good question. I speculate that the same would be true here, that, you know, there's no hard barrier and you can kind of push backwards in time by adding more and more of your relatively slow modes. And, you know, get more of the form factor at earlier time, which knows more about the details. We haven't really looked at that yet, but, you know, I think that can be done. I mean, one thing you can do, for example, in this Floquet case, is imagine you have some like fast time scale which you're integrating out, but then also you have a very weak Floquet drive. So it's almost a Hamiltonian, but with conserved energy, but you're very slowly losing energy. And that corresponds to this effective theory here, where you just add like a constant to this equation, because now you have some basically energy decay towards the center of the spectrum. And you can do the same calculation and you get a prediction which is modified slightly by that sort of decaying mode. It's now no longer diffusing, but just decaying. And you know, you can do some numerics and it agrees perfectly. So you can deal with such like exponentially decaying modes, and, you know, especially if there's special modes that are long-lived relative to the other ones, then you can see clear features. Like, for example, you can take a nice Floquet model is to take a pair of SYKs with not equal but correlated randomness and repeat them. So SYK1, SYK2, and repeat. And that's a Floquet model where you can analytically calculate the decay rate of energy. And you do spectral statistics of that using exact diagonalization. And the formula you get from our effective theory just perfectly agrees with the numerics. And again, all you're doing is essentially adding a decay rate in here that you can calculate into this diffusion equation. Or it's really like a decay towards infinite energy, but you can kind of deal with that in a reasonable way.
Yeah, thanks.
Yep.
Hi, I have a question too.
Please.
Yes. So in random, I wanted to know if there is any relationship to the fact that sometimes, you know, when one works with random matrices and describes everything in terms of like collective fields, like the density of eigenvalues, one can write actions for them that look like hydrodynamic actions. As if the density of eigenvalues is the density of a fluid, and there's some velocity associated to that fluid, and so I just wanted to know if there is any relation, or if you have thought about this possible relation.
Yeah, good question. Yeah, I would say we haven't thought much about it. There could be a relation. Well, there is a relation. I mean, I guess what you're essentially describing is like the hydrodynamics of the Coulomb gas.
Yeah, for example, in the simplest case.
Dynamics of that. So yeah, somehow you would need to like modify that hydrodynamics to incorporate the structure. Like that's what our hydro theory is doing. It's computing how you deviate from random matrix behavior due to structure in your system. So this would be like taking that Coulomb gas system and modifying, weakening the level of repulsion, the long level repulsion due to the presence of the structure in your system. And I think there should be an interesting way of doing that, but I don't see like a very direct connection to what we did. But I think it's an interesting direction to explore, in my opinion.
Thanks. Anyone else would like to ask a question?
Hi, yeah, I have a question. I mean, this might be a little bit speculative, I'm not sure. It's sort of like when I think about a cosmological scenario, right? So what happens during inflation is that inflation stretches out your modes, right?
Yeah.
And they leave the horizon, right? And the modes which leave the horizon, no, I'm sorry, the inflation stretches out your modes. And then when inflation ends, after that, modes start leaving your horizon, right? And the modes which start leaving your horizon, they freeze out. Right? So they correspond to the structure that has formed. Now, I mean, maybe I'm just stretching too far, analogy, but it sort of, when you were talking about that you have this system and you're talking about the equilibration of all of these modes, you're letting all of the modes relax one by one. That is a sort of picture that came to mind, and I'm not, it's very vague. It may have absolutely nothing to do with what you're talking about, but I thought maybe I'd mention it.
Yeah, I see. Okay, that's an interesting thought. Yeah, I guess my first instinct there is to say that, as you say, what's happening is that you're not really reaching equilibrium. Like you have these frozen fluctuations that are seeding structure. So we're like looking at one particular snapshot of the configuration which gets frozen in. And so if you had such a dynamics in some system, that would probably modify the spectral correlations in a different way. It's not really a steady state, I guess, but yeah, so yeah, if you don't reach equilibrium, like for example, in the case of glasses, you don't reach equilibrium, then you again get a modification of the story. So, for the thing you're mentioning, I can imagine there's an interesting story there, but you think you'd need to think about how to set up the situation in a nice way. But yeah, I think it could be an interesting sort of correction from the non-equilibration.
And otherwise, I mean, I just wanted to say I've been a very big fan of your work. And
thanks. Kind of you to say.
It's a great pleasure to.
Well, thank you. All righty. Well, seems like a good place to wrap up.
Yeah, I guess probably that's all for today.